Hello everyone, in today's video I'll introduce the second law of absorption process, that is Beer-lamberts law. So this law is extension of Lambert's law. So if you see the video of Lambert's law clearly, then you can understand this process more easily. Okay, so let us see the definition now. So when you're passing a monochromatic light through a pure absorbing medium, the rate of decrease of intensity with thickness is directly proportional to the concentration as well as intensity of incident radiation. So if you observe Lambert's law, this ratio is directly proportional to the I naught value. But here, this ratio is directly proportional to the concentration of solution as well as intensity of incident radiation. So concentration is expressed in moles per liter. So especially this Beer-lamberts law is used in case of solutions. Okay. So here D indicates a small change, decrease in small change, that is nothing but intensity, and X indicates a thickness. So this ratio we can observe that if I remove this proportionality, I'll keep the constant epsilon in the second step. So I got the equation 1. So after that I'll bring this I naught to this side and dx to that side. Then I'll get di by I naught is equals to E C dx, epsilon C dx. So I got the equation 2. Got an equation that is 2 di by I naught is equals to minus epsilon C dx. So if I integrate both sides between the limits I naught to I and 0 to x, then I'll get integration of I to I naught di by I naught is equals to integration of 0 to x minus epsilon C dx. Okay, so this can be on further step. You'll get that di by I naught is nothing but what? Log I. So log I naught to I is equals to minus ECX. So I converted integration to log now. So this can be written as log I by I naught, I minus I naught is equals to minus epsilon Cx. So we know log m minus n is nothing but log m by n. So log I minus I naught is nothing but log I by I naught. So I'll get that log I by I naught is equals to minus epsilon Cx. So I got equation 3. So now what I will do, by taking anti-log. So if I convert this log into anti-log, I'll get I by I naught is equals to e power minus epsilon Cx. So this, if I bring I naught to this side, then I'll get I is equals to I naught into e power minus epsilon Cx. So I got equation 4. We got an equation that is I is equals to I naught into e power minus epsilon Cx. So from this I'm calculating the intensity of absorbed radiations. Okay. So I absorbed radiations can be calculated by I naught minus I. So I naught means intensity of incident radiations and I means intensity of radiations after passing through the medium. If I subtract both, then I'll get I absorbed radiations. So here we know I value, this one. So I'm substituting here. I absorbed is equals to I naught minus I naught into e power minus epsilon Cx. So if I take common I naught, if I take common, then I'll get I naught into 1 minus e power minus epsilon Cx. Okay, this is equation 5. So now again I'm taking equation 3. Log I by I naught is equals to minus epsilon Cx. So by changing this logarithm, natural logarithm into base 10, then I will get 2.303 log 10 I by I naught is equals to epsilon Cx. So now this 2.303 I'll bring to this side. Then I'll get log 10 I by I naught is equals to minus 1 by 2.303 epsilon Cx. So 1 by 2.303 is considered as epsilon dash. So log 10 I by I naught is equals to minus epsilon dash Cx. So I got equation 6. So now epsilon dash is nothing but molar extension coefficient. Okay. So now I by I naught, if I bring this log 10 to this side, then 10 power minus epsilon dash Cx. So from this I am calculating the I value. That means intensity of radiations after passing through the medium with some thickness. So therefore I is equals to I naught 10 to the power of minus epsilon dash Cx. So I got I value now. Let us see the physical significance of E dash, that is nothing but importance of molar extension coefficient. Okay, so I'm taking equation 6 now. From equation 6, log 10 I by I naught is equals to minus epsilon dash Cx. So we got this equation. So from this I'm getting E dash value. So E dash is equal to minus 1 by Cx log 10 I by I naught. Okay, so this on further processing you can get E dash is equal to 1 by Cx log 10 I naught by I. It become reverse. Okay, so now what I will do, if log 10 I naught by I is equals to 1 and concentration becomes 1, then E dash becomes 1 by x. Okay, so if log 10 I by I naught is 1, concentration is 1 molar concentration, then you will get E dash value as 1 by x. But when it is possible, I naught by I is equals to 10. When I naught by I is equals to 10, then only you will get one value, because log 10 base 10 is 1. Okay, so but it is possible only when I naught by I is equals to 10. So from this I am getting I value. I is equals to 1 by 10th of its I naught. 1 by 10th of its original value. Okay, so finally I got I value. So from this I can define E dash, molar extension coefficient, as reciprocal of thickness of the medium when concentration is 1 molar, and in such cases intensity becomes 1 by 10th of its original value. Okay, so E dash is defined as the reciprocal of thickness of a solution layer of 1 molar concentration, which reduces the intensity of light passing through it to 1 by 10th of its original value. Okay, so this is about physical significance or importance of molar extension coefficient. Let's see the limitations. Okay, this law is obeyed only when the radiation is monochromatic. That means we should pass single colored radiations through the solution. If I pass dichromatic light, then there is a variation in the Beer-lamberts law. Okay, this law is not obeyed if the radiation used is not monochromatic. Next, it is applicable only to dilute solutions. Dilute means you should take very less concentration of the solute in this solution. If I increase the concentration, and again it changes the Beer-lamberts law, because Beer-lamberts law depends on both concentration and intensity of incident radiations. Okay, so in case the solute is electrolyte, if I use electrolyte like NaCl, if I add, it breaks into Na plus and Cl minus. These ions also undergoes interactions. This interactions changes the absorption process. Okay, if I use electrolyte or if I increase the concentration, then there is a variation in this law. Next, the temperature should remain constant during this process. If I increase the temperature, what will happen? The solution boils, and because of that reason it changes the absorption and it shifts the absorption bands towards longer wavelength. So too much temperature also changes the absorption process. So in order to apply this law, we should maintain the temperature constant. Okay, so and this is completely about Beer-lamberts law and limitations. Thank you so much for watching.